It's whatever you're comfortable with. So you're fine.
Small groups.
Yeah.
Just hang out. Okay, yeah, thanks for that intro, Rob. I'm excited to be here. Thanks for having me. I'm gonna talk to you today about a couple of my PhD projects. So this will be the structure. I think most of you are probably familiar with direct imaging, but we'll just give a little background in the beginning. And then two of my PhD projects are focused on the planet detection confusion problem in multi-planet systems and using solar system analogs to inform direct imaging observations. So some background in direct imaging, I want to make sure that by the time we're done with this, everyone's familiar with what it is, how we do it, and what future missions we'll look for. Essentially, when we're directly imaging a system, what we're doing is blocking the bright light from the host star. So in the center here, you can see an example of a ground-based image to resolve the light from an exoplanet's atmosphere. So you can see the orbital motion of this HR 8789 system because we have these many years of observations. We do this using a combination of techniques, including coronagraphs, adaptive optics, wavefront sensing, angular differential imaging. And these are very technically challenging observations. So our current best capabilities are coming from ground-based observatories primarily, who are imaging young giant self-luminous planets, which are primarily on long period orbits. And that's because these planets are much brighter in the infrared, so it's easier for us to see them, and their larger orbital period makes it easier for us to spatially resolve them. For this talk, I'm focusing mostly on future direct imaging missions. So Roman will be launching in 2026, ideally, and it will enable hopefully the detection of a couple mature Jupiter analogs in reflected light. We have future ground-based facilities like the extremely large class of telescopes, which will help on the ground, and then something like Habitable Worlds Observatory, which I'm sure we're all excited for here at Goddard. On the right-hand side of the slide, I'm showing you in the top table some example contrast requirements for a couple solar system analogs. And so you can see that to reach something like Jupiter and the Earth, we're really going to need contrast levels of about 10 to minus 9 or 10. And so in the bottom panel, I'm showing you an example of a currently observing systems, the Gemini Planet Imager, compared to some systems that we're looking toward in the future, including the 30 meters standing in for those extremely large telescopes, Roman, and then HABEX standing in for HWO. So we're going from contrast levels of about 10 to the minus 7 at best right now, all the way down to 10 to the minus 10 to get to that Earth-like planet. On this slide, I'm showing you a plot from the HABEX final report. So what you're seeing on the right-hand side are a set of simulated detections. This is a 3-planet system with a Jupiter analog, a sub-Neptune, and an exo-Earth. It's been imaged clearly 4 times over a year, so from March to September. And you can see that between these panels, there is some orbital motion. So you see the planets move between the images. So these advances in technology will enable the detection of these closer in planets, but it's also going to complicate our task of deciding when to observe the system. The reasons for that are that more planets per system might be detected. So with this orbital motion, we might not be able to immediately detect which planet is which. We have the potential for misdetections due to either the planets being within or outside the working angle of the instrument. Maybe their phase is too dim for us to detect. We might have some false positives like speckles, which mimic the planet signals. And then we also, for some of these systems, we could be doing a blind search, so we might not have precursor knowledge. So this leads me to the questions that I've been trying to address through my first PhD project, which is focused again on planet detection confusion. So in this section, we're going to look at how confusion will affect future direct imaging observations and how photometry can help us to actually address this confusion problem. So to introduce the confusion problem, some previous work, which was done by my colleagues and out of Carrie's lab at MIT, has predicted that we might encounter a confusion problem when multiple planets are detected per system, and this is over several observation epochs, so we're not sure which detection corresponds to which planet. And this figure here I'm using to illustrate that problem. So in the left-hand panel, you're seeing 3 detections of a 2-planet system. These detections are spread out equally over 1.2 years. And the confusion problem here lies in the fact that there are 2 ways that we can fit orbits to this system. In the middle panel, you can see a relatively coplanar system with low orbital eccentricities. And on the right-hand side here, you can see it's obviously no longer coplanar. We've got higher eccentricities, and the planets are actually slightly closer together. So the issue here is that these two sets of orbits provide equally good fits to the data. And that means we need to consider some other methods on top of that relative astrometry to decide which set of orbits best fits the system. So my colleagues developed this tool that we call the deconfuser. This is an algorithm that was designed to rapidly assign detections to planets and to perform an assessment of the confusion problem. So here I'm just going to walk you through the flow of the deconfuser, where first you feed it that relative astrometry or those detections like we just saw. And this results in many possible combinations of orbits. So you still need to decide essentially which set of detections is fit to which planet. What the deconfuser does is then it finds the combinations of orbits that best describe the detections. And so it does this using a 3D grid search over the orbital parameters. So it searches over the space of semi-major axis and the x and y vectors of the eccentricity. Then it keeps only the orbits that fit within some astrometric tolerance that is set by the user. And it ranks orbits based on those that have the highest number of matched detections. So for example, if you have an orbit option that fits 3 out of 3 detections versus one that fits 2 out of 3, your 3 out of 3 will be ranked higher. And then at the end of this, what you get is a list of top ranked systems, but you might still have multiple groupings of detections per planet, which are self-consistent and describe the data equally well. And so this is the stage really where we can introduce some other information on top of that relative astrometry to further refine the equally ranked orbits. You might also be wondering how the deconfuser is different from traditional orbit fitting methods. So here I'm going to compare the deconfuser to a very well-used and widely known tool called Orbitize. As I mentioned previously, the deconfuser fits orbits with a 3D grid search. So again, over the search space of the semi-major axis and the x and y eccentricity. Something like Orbitize performs iterative fitting. So it uses Bayesian methods and draws trial orbits from prior distributions. And something like Orbitize is guaranteed to either converge to the correct posterior of the orbital parameters or to find a solution within the astrometric tolerance if it exists. The issue with that is that there are regions where these solutions lie that could be potentially numerous and very small. And so you run into the issue where you need a large number of samples to ensure that all confusing orbits are found. And so when my colleagues ran tests against the deconfuser compared to Orbitize, Orbitize was not always able to find a solution within a few seconds compared to the deconfuser, which can. The deconfuser also touches on efficiently handling poorly conditioned cases. So what I mean by that is this example in the middle panel where you have these very different sets of orbit combinations, which can equally fit these 3 detections. The efficiency then makes it fast enough to perform Monte Carlo studies of many systems, and we're able to study the confusion problem that way. And then standard orbit fitters, they don't actually address planet detection confusion, so you have to know which planet is which before you do the orbit fitting. What I'm showing you here is the current performance of the deconfuser with only astrometry. So on the plot here, we have the probability of confusion as a function of the number of times you've observed the system, and then also as a function of the system inclination. So you can see that for low system inclination, for something that's face on, you have a very relatively low probability of confusion. And then as you start to increase that system inclination, your probability of confusion grows. And when you get to something that's nearly edge on, you have a probability of confusion greater than 40%. So this is the scenario where we can start to bring in something like photometric information. And what I mean when I'm saying we're going to use photometric information is basically taking the information that you get from the phase variation as the planet is orbiting the star. So just to provide the definitions that we're using for phase angle here, we call the phase angle of 0 degrees when we have the day side facing the observer and you're directly behind the star for an edge-on system. And then 180 degrees is when you have the night side facing you. So we go from 0 degrees at its brightest to 180 degrees at its faintest. And so we know that this brightness variation, of course, changes the contrast ratio between the planet and star. It also affects the albedo spectrum and the color of the planet. And so my work has essentially focused on augmenting the deconfuser with photometry to consider those changes in brightness throughout a planet's orbit and to assist in breaking ties between equally ranked orbits in the deconfuser. To do this, I have developed a photometry model where we calculate the expected phase angle of the planet given that orbital geometry determined by the deconfuser. And with the phase angle, then we can calculate the phase function, the contrast ratio, the expected planet brightness, and that gets us to this measured brightness here. So on the bottom left hand. When we have a measured brightness, this is where something like ranking orbits can come in again. And so with photometry, we can provide scores to orbit options that are returned by the decompuser. And then we can compare the likelihoods of those scores for the measured planet brightness to, and for each set of orbits to rank orbits higher if they have a more statistically likely phase or brightness result. So here I'll just walk through how we take the output from the decompuser and incorporate photometry. From the decompuser, essentially what we get are the orbital parameters for the system. So we have the planet to star distance vector and the planet to observer distance vector, which we can use to calculate the phase angle. We can then feed that phase angle directly into the phase function. So for this initial work, we're just using a Lambertian phase function. This approximates most planetary phase functions relatively well for this work. And then we can feed that directly into calculating our planet's flux density. So we prescribe some geometric albedo, we have our phase function, prescribe a planetary radius and some stellar flux. And then that, of course, also feeds directly into our planet count rate of the detector. So in order to rank orbits based on a detection's brightness, I need some distributions and some likelihood functions to work with. And so I need to ask, what is contributing to the photon count overall when we're directly imaging a planet? So here we've already talked about the host star contribution and the contribution from the planet. I've also designed a basic detector noise model using the parameters that are laid out for Roman. We chose Roman because it has been the most extensively modeled chronograph instrument. And so we use the parameters for Roman to do our noise simulations. So now I'm going to walk you through the steps that we take to actually get to the likelihood of these orbit fits. The noise model I'm representing here as a Poisson distribution. So essentially your output from the noise model is a probability density function, which describes the electrons that are read out by the detector. In the actual code, the distribution here is basically a combination of a Poisson distribution for the photon noise, a gamma distribution to model the EMCCD, and a Gaussian, which describes the read noise. So then we have our expected number of photons to be received at the detector, which I'm calling NP here. This, of course, depends on the number of photons reflected by the planet. We also saw that it's dependent on the phase angle and orbital parameters. It's also dependent on our observing instrument, so the integration time here, and the background contribution. So each planet has a unique photon count due to its orbital parameters and your instrumental parameters. So then for each detection, the probability of measuring a certain number of photons, given those orbital parameters, is described by a probability function. Of course, we need to consider each set of planet detections together to determine the overall orbit likelihood. And so the likelihood of measuring all detections, given the parameters of the matched orbit, is the product of the individual detections, because we're considering each detection to be an independent event. So here is our likelihood function, where J is our number of measurements. I'm going to skip a few steps in the algebra here. So at the end of this, our probability distribution follows the photon distribution, distributions caused by detector noise. We can plug in our number of photons expected from the planet, apply a natural log, and we end up with this log likelihood function, which we can use to rank orbits. So now we have the steps in place to place refine orbit rankings by the decompuser for systems that are particularly confused. Put together, it looks something like this, where we again take those output orbital parameters, we feed them into this photometry model, calculate our phase angle and brightness, add those detector properties, and then we end up obtaining a likelihood for each detection, combine those for all of the orbit fits for the system, and then we refine our orbit rankings based on those likelihoods. So now I'll just walk you through one example system of what that looks like with photometry. So here you're seeing again on the left-hand side some system detections. This time we're looking at a 3-planet system, and it has been observed 3 times spread equally over 1 year. And then these 2 orbit options are what the decompuser has returned, given only that astrometric information. So you can see again, we have relatively coplanar in the middle, something a little bit funkier on the right-hand side, and then we can essentially calculate our expected brightness given these orbital parameters. So when we compare the likelihood of option 1, given the detections, to the likelihood of option 2, In this scenario, we end up with the likelihood of option 1 being higher than 2, given that photometric information. And because these are simulated systems, we can compare option 1 to what the true system parameters look like. And so the good news here is that on top of being deconfused, we have chosen the system which more closely resembles the true system in this scenario. Now with the deconfuser, there's also a lot of future work that we can do. We could move towards something that is more similar to a more traditional orbit fitting method, where you're using orbital parameter priors to better constrain your orbits. We could consider only systems which are mutually inclined or account for the dynamical stability of systems. Another area that we've discussed investigating is the effect of null or misdetections or false positives on confusion rates. And then the part that I'm most interested in personally is planetary color. So how does multiband photometry actually assist in deconfusion? Okay, so in part 1, we've taken a look at how confusion will affect direct imaging observations. We've seen that it will make it difficult to differentiate which detection corresponds to which planet, and also that the probability of confusion grows with the increasing number of planets and inclination. But the good news is that photometry does actually help us to address the confusion problem. Ranking with photometry will help us to reduce confusion, especially for highly inclined systems, which are the most affected. And then inclusion of color and spectral considerations, we also expect to help us improve the problem, because there have been a lot of previous studies on how color varies with the phase angle. And I can pause here before I move on to part 2 if there are any questions on part 1.
I do have a quick question for you, Sammy. Seems like there's a degeneracy between the eccentricity and sort of the inclination of the plane of the orbit. Is there a way to solve the degeneracy, or is that just something that's always sort of built in and limited there?
That's a good question. I do not know if there's a direct way to solve it within the deconfuser, but I have noticed that there are often orbit options that are returned that are maybe something that we shouldn't expect to see normally. But yeah, something we need to look into.
Is there a plan to include more orbital parameters? So I know like usually if you're using orbitides, you'll have like 6 parameter basic sets.
So I guess because I mentioned the 3D grid search, it does fit the other 3. It just uses a least squares fitting method to fit them.
Yeah.
Got Rob.
So I'm curious, how good does the flux calibration have to be to accurately use the photometry?
That's a good question. We have not looked super deeply into it yet. As I mentioned, we're using Roman parameters, so the throughput is not super great in our model. But yeah, I'm not sure. We haven't done a deep investigation yet.
Can you go back to your test system?
Yeah.
For the
This one?
photometry, and so in the case of this second epoch, you have 2 planets really right on top of each other. Have you tried just for fun seeing what happens when you say, well, I claim there's 1 detection and I have biased high photometry for 1 planet?
Oh,
Like,
that's a good question.
What comes out of that?
We have not tested that yet, but that's definitely something we need to look into. Yeah, I think that would probably fall under our category of like false positives and that investigation.
There's a question online, but I think your speaker might be muted if you want to unmute that.
It doesn't say that it's muted.
Oh, it's not. Okay. Avi, do you want to go ahead?
Yeah, can you hear me now? Is that all right?
Hold on, Avi.
Nope.
1 second.
Can you
Okay.
can you hear me?
Oh, no.
It's weird.
But yeah, it's coming through.
It's weird.
I think it's coming back.
And yeah, your volume's up on your computer.
Yeah.
Okay, let me just try and see.
Okay, thanks, Nicole. Nicole can hear me online. So, but
Okay,
I
yeah,
guess-
Avi. There might be a little bit of feedback if you go ahead.
Okay, I do hear feedback on your side, but okay, yeah. So I was wondering about the statistical fitting routines they use and whether they can incorporate uncertainties in those positions and whether you use a Bayesian strategy or something just like least squares, or how that kind of scales with the number of data points and uncertainties and so forth. It's challenging.
By uncertainties, do you mean in the orbit fitting generally?
in the position, so for X and Y, obviously, I mean, the points look like you're using like a perfect value for every single point when you'll have, you know, either due to PSF uncertainties or something like this, the actual position or some background or whatever it is, other position uncertainties. And then you have uncertainties in the photometry, the color, and so forth. Is there some? I'm just wondering if you have some kind of grand statistical analysis strategy, or whether this is, you know, whether you're starting with at least squareds, or I'm just wondering what your strategy overall is for that.
Yeah, so in the relative astrometry, there is like an error tolerance, and you can incorporate in the simulated detections some level of uncertainty. In the photometry, that we don't yet have uncertainty included, but that is something that we're doing next. And so our plan is to, on a more basic level, first introduce kind of like a scaling metric, which scales your photometric uncertainty, or it scales your astrometric uncertainty based on your photometry. So if you have a dimmer phase angle, your astrometric uncertainty should be higher, and vice versa. Does that answer your question?
Yeah, I think so. All right, great, thanks. We can talk more later.
All right. So I will move on to part 2, and we can do more questions later if we have them as well. So now I'm going to move on, kind of coming back a little bit closer to home, and we're going to talk about the ice giants in the solar system. So we're going to look at how the ice giant atmospheres reflect light at partial phase angles, and then also how the ice giants can help us to understand ice giant-like exoplanets. So I'll start with a little bit of motivation for the work. Firstly, the main point is that exoplanets will only ever be imaged at partial phase, right? So I have 2 example systems here to illustrate that, BetaPic on the left and HR 8799 on the right. We have BetaPic on a closer to edge-on orbit, which is, if we were looking at reflected light, we would see a lot of phase variation. And then something like HR 8799, where you're seeing the planets only ever at partial phase. And on top of that, we have our inner working angle, which will block our brightest and dimmest phases. So we can study the solar system planets in exquisite detail, which is something we obviously won't obtain for exoplanets. And Laura Mayorga is someone who spent a lot of time thinking about this. And so here we're going to look at an example plot from her 2016 paper, where she essentially reanalyzed some observations of Jupiter from Cassini. So in this plot, the black points are the Cassini data points, and we have some model phase curve fits. And so what Laura found is that Jupiter was significantly darker than a Lambertian phase curve at partial phase angles, and it was also not well fit by Jupiter-like exoplanet phase curves. So if we compare it to something like the Lambertian, which is kind of the darker red line, you can see that at lower phases, Jupiter is much dimmer, and then at higher phases in some of these filters, Jupiter is actually brighter than Lambertian. And then compared to the Rayleigh scattering, which is the gold line, and the kind of single scattering phase functions, they're also not super well fit. And so results also from this paper were an update kind of on previous Voyager observations. And so Laura found that the bond albedo also was significantly revised from 30% to 50%. Additional motivation, of course, is that ice giant-like exoplanets are among the most common planets to have been discovered to date. So I'm illustrating that with the surface gravity versus bulk density plot here, where the ice giants in blue carve out this distinct region of space compared to the gas giants in orange, or something like terrestrial planets where the Moon and Mars are plotted for reference. And so, of course, future observations will seek to constrain the bulk composition of these planets' atmospheres and understand their processes. And this was specifically called out in the decadal survey. So how can we place these planets within a continuum of our understanding of substellar objects? So the data that we used for this work was from the New Horizons mission. You are probably most familiar with this mission from its beautiful Pluto system images. New Horizons was launched in 2006. It did its Pluto flyby in 2015. It's now in its second extended mission, so it's over 61 AU from the sun. And it's at this very unique vantage point to look back at the solar system and provide these high phase angle observations. So in 2023, New Horizons multispectral visible imaging camera observed the ice giants at high phase. We had a dedicated imaging campaign. In the table, I'm showing you some of our observation details. So you can see we have 6 scans of Uranus from 2023 and 36 of Neptune. And so the top right-hand side is showing you the viewing geometry with respect to New Horizons. And then I have a subset of some of our data here. So these are Uranus observations. We have 4 filters on MVIC, which are blue, red, near IR, and methane. And so we had relatively good detections in the blue and red filters. We have a pretty weak detection in near IR, which you can kind of see in the middle here, and then a non-detection in the methane band.
What phase angle was?
This is for a phase angle of 44 degrees.
So the drawing at the top left is accurate for the photo?
Yes.
On the slide?
For Uranus, yes.
And no methane detection. Interesting.
It's pretty faint. I have a spectrum later that we'll look at. Yeah. Yeah, so the other unique feature of this work is that we have simultaneous observations from Hubble. And so on the left-hand side, I'm showing you some of those for Uranus, going from bluer to redder wavelengths from the bottom to the top. You can see that the polar cloud feature starts to become more prominent. And then we just have these nice 3-color maps for both the rotation periods that Hubble covered. We also have some simultaneous observations from ground-based community observers. So Susan Beneke, who's on the New Horizons team, led the solicitation and a collection of these. Most of these images were submitted as JPEGs or PNG files. They're mostly context for the New Horizons observations, but they do cover longer baselines. So we have images from both before, during, and after the New Horizons observations. Now, I'll just kind of briefly walk you through our data reduction method. So the data that we did receive from the New Horizons team was level 2B data, so it was mostly already processed. There were some striping artifacts that we had to remove, and then we, of course, had to identify the planet location. As you saw before, it was just a couple pixels that we were looking for, so we had to correct for the slight error in the pointing. Then we performed aperture photometry, converted those counts to our radiance factor or reflectance. And we did this just by accounting for the spatial scale, walking through these equations on the right-hand side. We use a particular filter keyword for each of the filters to convert the data, and then we end up with this reflectance value. So I'm going to focus just on the Uranus results because we published those at the end of last year, and we're still working on the Neptune analysis right now. What you're looking at here is essentially the reflectance as a function of the sub-observer longitude for New Horizons. And so the main takeaways here are that in the red and blue filters, where we had our strongest detections, there was no statistically significant rotational variation. And then because we have those extra data points from 2010 and 2019, we can also compare longer baseline. But we also did not see any statistically significant variation from 2010 to 2023. So here I'm showing you the empirically measured spectrum from the ground. This is from Prakash 1998, and it has been scaled by that Lambertian phase curve. And so we have the 2023 observations would follow this dark line, and then our additional scan for 2019, I believe, is the 52.4 degrees, is the dashed line. We also have the Hubble photometry that's been scaled here. That is the triangles on the plot. And then we have some what we expected to see from New Horizons with the squares. And so our main takeaway for this work is that Uranus was dimmer than predicted by a Lambertian phase function in the blue and the red filters, which is not a huge surprise given what we saw for the Jupiter analysis from LoRa as well. But we can also see what this might look like in terms of exoplanets. So if we scale the axes now to contrast ratio, we have Uranus at its current distance on the left-hand side. And then if we kind of arbitrarily scale the planet in to make it brighter at 6 AU, we reach contrast levels around 10 to the minus 10. So to emphasize a few points for exoplanets, of course, we need to understand the atmospheric scattering very well in these near quadrature regimes. That's also obviously important for understanding Uranus itself as one of the least understood planets in the solar system. And these multi-epoch observations at many phase angles can help us to broadly constrain the energy balance of the planet when we have multi-band observations. We also need to make sure that we are considering more sophisticated phase functions when we are doing our atmospheric modeling for exoplanets. And also fainter exoplanets might require more sensitive instruments or longer integration times for detection and characterization. Okay, as I mentioned, the Neptune analysis is still in progress, so I'm just going to show you a couple of nice pictures here. On the left-hand side are some of those ground-based community observer images. So We do have longer baseline coverage again for Neptune, which is nice. And then the 3 color maps from the Hubble images here. And you can see that there is already a little bit of cloud variability. So we'll see if we can tease that out of the photometry. So we've taken a look at how the ice giants reflect light at partial phase angles. We saw that Uranus is dimmer than predicted by Lambertian, and also there was no rotational variability due to that lack of large-scale cloud variability, which we expected from the context imaging. We've also taken a brief look at how the ice giants can help us understand ice giant-like exoplanets. So the solar system planets, of course, provide this really necessary context imaging, and we should continue to do these analyses into the future. And of course, understanding the energy balance of the planets within our solar system will help us to better extrapolate for understanding exoplanet observations. And we're about to the end, but I did want to just kind of briefly plug some other science that I've been working on over the last few years. The first is something that I started as visiting graduate student at IPAC last year, so working with the Roman team. And this is a question that I think is really exciting. So we're looking at the feasibility of imaging a ringed exoplanet with Roman. So on this plot here, I'm showing you some spectra of Saturn. So this is at a phase angle of 90 degrees with the rings inclined by 20 degrees with respect to the observer. And you can see that the difference between the planet without rings and with rings, we have quite a significant variation in reflectance. So there's actually a greater than 30% increase in reflectance in these relatively visible wavelengths. So we did kind of a first case feasibility study of whether or not this would be visible with Roman by injecting a Jupiter analog at 15 parsecs without rings, and then one with an increase in reflectivity. And so the kind of interesting and exciting thing here is that there is an increase in the core of the PSF here. And so we hope that a ring of some size would be detectable, but this is still ongoing work. Then
Really quick question.
Yeah.
Is that the speckle pattern at the center of the image of the star and the planets to the top right?
yes, planet is at the top right. Yes.
Thank
you. And then kind of off to the side, doing some not exoplanet related work. I worked with a team at MIT with Julian DeWitt to basically maximize the science return of some transit observations. And so we developed some pipelines for ground-based observatories to essentially run this shift and stack technique to recover very faint objects and observations. So I'm showing an example of what one of those completed shift and stack images looks like. So in the center, you have a very faint asteroid. These streaks are our stars in the field. And then recently we had a paper published where we were analyzing a TRAPPIST field of JWST observations. So we were actually able to recover almost 200 unknown decameter-sized objects in the asteroid belt. Okay. So with that, I will not read you through my summary since you've heard most of it already. But if you are interested more in the ice giants work, the link to our paper is in this QR code here. And I'm happy to answer questions or chat more about any of it.
Excellent talk, Sammy. So yeah, we have plenty of time for questions. So anyone in the room, feel free to raise your hand, or you can raise your hand online or post your questions in chat. It seems like we have NASA has devolved to Telegram levels of technology here. So for the folks online, if you unmute, we might just have to do a little bit of a pause so I can mute and unmute to avoid some feedback. But any questions for Sammy?
So to make another plug, Joe sent out yesterday the link to sign up to meet Sammy. Sammy's schedule is mostly pretty full, but if folks want to chat with her more, like Robbie, if you want to talk about the transit survey that you're doing with Roman, you know, some time to meet Sammy. That'd be great. Sorry, putting you on the spot there, Robbie. That'd be great. Just go to Joe's email. Thanks, folks.
Anyone have any questions right now?
Are there any ideas for whether these albedo darkening or Lambertian deviations could affect planets that are like warmer than Jupiter? Like if you, in other words, like moving a planet like Jupiter close to the sun, the star, would you expect the same physics to operate in terms of how it changes the Lambertian characteristic?
That's a good question. I think I would expect differing from a Lambertian in terms of the phase curve, especially at partial phases. I'm not sure exactly what the atmospheric physics would look like, but that's definitely an interesting question.
Are you gonna release the decomputer as like a, competing orbit fitting tool?
Well, so the decompuser is publicly available without photometry. Photometry is coming soon. We're planning to submit the paper next week, hopefully, and then should be available soon.
Sammy, you mentioned that you could also use planetary color potentially implemented in some of the degeneracies. How does it exactly work?
Yeah, well, I don't have an example. So color tends to vary. I wish I'd put a plot in here. With phase, and it kind of creates these like distinct loops depending on the planet and color space, or just like kind of drag across color space. And so you have both between planet types and also with phase variation. And so I think it will help us quite a bit more with different planet types. So you see like ice giant like planets, for example, are usually in like a bluer region of color space compared to gas giant like planets. And I think that being able to, so if we have say 2 points that are, one is much bluer than another, which is maybe more red, that should help you inform your orbit like pretty easily. If you have an orbit that's fitting both of those points at the same time, it maybe would be rejected over something that doesn't fit the 2 points.
Because that would tell you about the planet, effectively something about the planet mass or type, then that would tell you something about the orbit.
The planet type, yes. So you, ideally you would not want to fit like 2 different type planets to the same orbit, right? Does that make sense?
Because you expect the planet mass to have to be the bearing where it's orbiting.
Yes, yeah.
Another question, sorry.
Okay.
Why such the tentative or low detection method? So I would have expected that to be a lot brighter there.
Yeah, part of the issue is that so the observations were, I think, 0.7 seconds. That was the integration time. So super short exposure time, which I don't think, we did not have a say in that. If we were able to go back and redo it, we would definitely expose for longer.
That was New Horizons.
New Horizons, yes. Yeah, that's most of the problem, really.
Thank you very much. You mentioned this offset of 30% with and without belt or discs.
The ring exoplanet?
The ring,
Yeah.
sorry. And do we have any other observer we can use to know if this 30% are due to this or to other stuff will be?
Yeah, so rings do create some polarization signatures. I cannot remember the exact deviations off the top of my head, but polarization would be a good way to test whether they are rings or not. Otherwise, the scattering functions are quite a bit different. So if you are able to get multi-phase observations, your phase functions should look quite different. Even if you have like a face-on ring, you end up with this like double peaked phase curve, whereas like other phase curves are mostly one smooth peak.
Okay. And my other question is that this 30% in the case when it's a maximum variation or
That's a good
depending
question.
the inclination of the planet?
That's a good question. I am not sure what the variation looks like for other inclinations, which is actually something that I'm interested in doing a bit more of. No one has really looked at the inclination variation from the Cassini observations, and so I'm not sure if we really know the answer to that very well.
Okay.
I have a quick one. If you don't mind going back to your plot with the 3, the example system with the 3
Yes.
sub figures.
So
Yes, that's perfect. So I don't know anything what I'm talking about. I don't believe
That's okay.
planets are real. But have you does this model would it work for circumbinary systems where you have 2 stars? Would anything change in that regard?
Not in the information that you're feeding to the decompuser per se. So really all that you're giving it is those like planet detections. So the squares and the triangles.
Okay.
I guess if that changes your knowledge about where those are at, then that would affect your orbit fits.
Okay.
Mhm.
I gotcha. Very cool.
Mhm.
Awesome work.
One more.
Yeah.
So I think I've asked you this before, but like the null detection thing is always, in the background. So have you run this with just like deleting data points?
I have not. I think that, do you know Leonid?
Yeah.
I think he did like a very brief dive into it. And essentially it would make confusion worse, of course. But yeah, I have not done it personally.
Okay. Yeah, it sucks.
Yeah.
Actually, I have another one.
Yeah.
if you, if your system happens to have any sort of mean motion resonances, particularly closer into the star, can you feed that information in to help sort of suss out some of these other parameters?
That's a good question. So in current version, no.
Okay.
But that can be added to our laundry list of things to
Sure.
improve.
Very cool. Any other questions online?
But I want to take up all of Sammy's time.
We'll go for it. Give us the final word if you have one.
The final word.
Yeah,
The stakes high there, Jay, thanks.
no. I tried.
So Sammy, on your study for looking at adding rings to like a second life planet. So I'm assuming the next step is then to take that to CGI and see
Yes,
how we can then detect. So do you have any sort of spoilers you can sort of give us, like?
I don't, yeah, it's,
Contrast ratios?
unfortunately, I had to set it aside in term to do my thesis work.
Darn.
I know. But yeah, we're hoping to get there. At minimum, we want to be able to provide contrast limits. So
Yeah, because it's kind of sad to see that we can't detect Uranus or Neptune with
yes,
CGI, well, half worlds for sure.
Mhm.
Be cool to see if we can actually distinguish between rings or not rings of CGI.
exactly.
Pretty awesome.
Yes, or maybe it will help us detect other planets if there are rings.
Awesome. Well, excellent talk and excellent work. So let's thank Sam again. And then, yeah, feel free to get in touch with me or Rob if you want to meet later this afternoon. But thanks everyone for coming out in person and online. See something in chat. Oh, people are saying thank you, great talk. So I'm going to end the meeting for the folks online. Thanks a lot.